Hi guys, welcome back. This is our second video in this series of Simulink. We are going to solve a simple hydraulic circuit using Matlab. For simplicity, I've already opened my Matlab and inserted a screenshot of this section here because this is our main section so as to save time. Yeah. Therefore, we need for this one, we are going to use in our first video we used electrical library, but now this time we are going to use hydraulic library. Okay, yeah, for this hydraulic ones here, I illustrated how you can use electrical, but we'll come back here later. Let's now go to the next hydraulic. Therefore, we need to go. We have this the elements. Those are the sensors. Those are the sources, and those are the utilities. Okay. You can see here we have a tank and a pump. Then you have a block that represents the fluid inertia and a tube that represents the resistances to flow available in the tube and back to the tank. Therefore, the tank is our reference. If you go to the elements here, this is the reference our tank. And let me put it here. Okay, tank here. I will zoom in here. That's my first one. I can also, yeah, okay, let me just zoom in here. Then we need inertia and a pump. In this scenario, I'm going to use a pressure source because you can see this one is written pressure source. Therefore, you go back to the Matlab library. You go to the hydraulic sources here and look for the pressure source. Here it is. Drag it here. That's my source of the pressure. We usually connect T to tank. Okay, that's a T to tank. T means tank. This is a P port, and this is the signal port. This is a signal port that controls the P port. Okay, therefore the value at P port is directly proportional to the value at S port. That here is where you put your control. Okay, but now since our pressure, we are going to assume our pressure here is constant. You can see it is 1 megapascals, meaning we don't need this S. Okay, whenever the pressure is variable, always use this one, but now it is a constant, therefore I'm not going to use this, but I'll use this. I want to illustrate the reason why I'm using this. This one is now for constant. You see the word constant here. Remember this one, it is a pressure source, but it is 1 MPa. 1 MPa doesn't change, it is a constant. Therefore, delete that one and you attach this one back. Yeah, we have to retouch them back. Therefore, this one I can delete. Understood? Let's now continue. We need what we call fluid inertia. This one is a fluid inertia. I'll illustrate what the fluid inertia means. Go to the elements and take the fluid inertia block. Put it here. Let's double click here. Let's go to help. I want to understand what the fluid inertia means. Okay, pressure differential across tube or channel due to change in fluid velocity. Remember, pressure is velocity is a factor that contributes to pressure. Whenever there's a pressure change, you can see differential, you can be able to capture that by fluid inertia. Okay, and this is the formula here. The fluid inertia block models pressure differential due to change in fluid velocity across a fluid passage of a constant cross-section area. The pressure differential is determined according to the following equation. The P is the pressure differential, rho is the density, the length, you have to give the length of your pipe L, and the cross-sectional area. Then you give the flow rate over the time. Therefore, it is used to capture the pressure drop due to the change in fluid velocities by fluid inertia. As we go deeper, we'll use more examples. We'll understand as we proceed. Then we go back, we need hydraulic resistive tube. Okay, go back to library. Here it is. As the word suggests, it is a resistive tube. Okay, this block models hydraulic pipelines with circular and non-circular cross-sections and accounts for resistive property only. To account for local resistances such as beds, fittings, inlet and outlet losses, and so on. Therefore, because whenever you design your hydraulic lines, you might have some bed, some junctions, which contribute to loss of hydraulic pressure. You have to capture all those losses in this block. It captures all of them. Okay, as you can see from description, I'm using the description to assist me explain. Therefore, then this one, it is a complete loop, a closed loop. Go back now to T. Understood? But now, let me go back here. We have already modeled this, but we need to know the flow rate. We need to know the, I want to capture flow rate and I want to capture the pressure. Okay, let's see how we can now do that. The first thing we need to understand is we usually say flow through a pipe. Therefore, flow rate is a through variable. We usually have two types of variables in any system, that is through and across. Through is like a flow rate, current, torque, but across is like a voltage across, pressure across. Okay, therefore we need what? We need a hydraulic flow rate sensor. Go back to library, go to sensors, hydraulic flow rate sensor, like that. Remember, it is a flow rate, therefore it is a through variable, therefore I have to connect it through. Just the liquid has to go through this. Okay, then connect this one. Let me now illustrate. The Q port is where we get the value of the flow rate. This one, it has three ports. The Q port gives you the value. B port, it is the flow the liquid has to flow from A to B. Therefore, A to B. Therefore, you connect A here. This is the path A to B. You can see. But now this is the sensor that gives you the flow rate. M gives you the mass flow rate. Leave it for now because you need just how many. We just want to know how many liters per second. Then we need to convert this one. Always convert it because we need to use a scope. Okay, scope here like that. Then this a name. Leave it like that. Then we need pressure across A and B. Remember, due to the resistances here, the pressure gets generated. For example, whenever you move from high from a bigger cross-sectional area to a smaller cross-sectional area, there's some variation of pressure. Okay, and we want now to capture, because of this resistance of this tube, what is the pressure here now? How do you do that? Go to library. Now there's a pressure. Okay, remember I said the liquid go the pressure is we read from A to B, but P is where we get the value A to B. Therefore, let me rotate this once and control I to interchange B and B. This is a pressure. I have to connect it here, A, then B here, like that. Let me delete this, like that. Then I need to convert. Always use convert that one. Then we need to get this value here, like that. Okay. Remember, we are getting Q, which is L per second. Yeah. Q, that is L per second. That is Q, the flow rate of liters per second. Here we are getting pressure in megapascals. How am I? Let me see how I can define here. Just double click here. You go. You cannot choose the units inside. I can also decide meter cubic per second, blah blah. But now this one default inherit means they get the value here and converts directly. It is usually liters per second here, and here it is megapascals. Then we need solver. We have never ever forget solver. Never ever forget solver. Okay, like that. Then we need to define the liquid. How do you define what you are using here? You go back to library, you go to utilities, not utilities, hydraulic utilities, you take the fluid now. This is where we define the type of fluid, coefficient, parameters. Therefore, let me see whether they are defined. They are not defined. Okay. Therefore, we are going to maybe define the parameters here, and let me use default parameters. I'm not going to change here. Here is where you define the, for example, the fluid density, kinematic viscosity, bulk modulus, all these parameters you define here. Okay, but I'm going to use default parameters. Okay, pressure one. Remember here it is M1 MPa. Let me use 1 MPa like that. Okay. Next is fluid inertia. Next is fluid inertia. Let me see what it is. We don't have any value for parameters, don't have any value for the fluid inertia. Therefore, I'm going to leave it as default. Because I can see the parameters here for the fluid inertia. Okay, let's leave it as a default. So you don't define anything here. Then we need to define resistive tube. Okay, our resistive tube, we can now have a circular or non-circular here, but mine is circular. Let me go back here. We have these parameters: tube internal diameter 3, tube area 7, tube length 1. Okay, tube internal diameter, so it is 3.03 meters. Laminar friction constant for the key friction factor. Leave this one as a unless defined leave it default. These parameters are already tested. These are just theoretical theories behind the probe. Leave them as a constant unless defined. Tube length, we have said it is 1 meter. 1 meter here is 1 meter. Default. Laminar flow 2000, turbulent flow 4000. That makes sense. Okay, leave everything unless defined. Okay. Last three, we need to define solver time 1 second, and we need solver all day to 3t. Time here to be 1 second, 1 second, and we need the solver type to be OD to 3t. How do you change the solver? You go to model settings here, model settings. We want to change the solver to OD to 3t. In the near future videos, I'm going to illustrate where and why we use a certain solver, but for now, just for the for now we'll be using OD23T, and sometimes we'll be using OD15S most of time. Okay, and sometimes OD23S, but not as OD23T. It is just a method used to solve the matrix equations, algebraic equations. Depending on the type of the solver, you get a different answer, though the differences is just a small value. I'll make a video to illustrate one by one in a deeper details. But for now, that's not so important for now. I think we have defined everything in our model. Go back to simulation, run. Let's see the values here. There's a problem. There is a problem here. You can see there's a QS zero pressure. This doesn't make sense. Let's now try to troubleshoot and see where we went wrong. The first one, I want to change the layout to 2 like that, so that we can compare Q. You're getting a Q of 0. Okay, let's see the why. I need to determine the fluid inertia first. The fluid inertia. The passage area here we didn't define. We forgot to define this as indicated here. This 7. Yeah, we are supposed to define it. The passage length of 1. You define here. Okay. Therefore, that's what we forgot. We forgot to define 7 a negative 4. That's what here. Let me see. Yeah, now this makes sense. As you can see, when the flow rate is constant, the pressure is constant. That's how intuitively you can be able to validate whether your model is behaving well. You see, the higher the flow rate, the higher the pressure, but both becomes constant. That makes sense. Okay, thanks so much, guys. Let's see you in my third video. I'm going to display something amazing. See you in my third video. Bye.